Now we need to talk about the other type of depression, the large-scale low pressures. These are otherwise known as polar frontal depressions. They are created in a very different manner than the small-scale heat lows. The polar front depressions are found along the polar front itself. This is principally in the higher latitudes, at about 40 to 60 degrees, depending upon the season. They typically move from west to east across the globe. The process of their formation is complicated and a little involved. Essentially, there are two main processes that need to occur to create a mature polar front depression. The first is to do with upper air movement, associated with fast currents of air, called jet streams. If we look at an example in the animation, we can see that the flow converges and narrows. This narrowing causes the velocity of that airflow to increase. The effect of this is complicated, but it is sufficient to say that as a result of this, there are areas where we have net loss and net gain of air in the upper atmosphere. These can be split into zones, labelled A and C. In the areas labelled C, we have a net loss of air. In other words, air wants to leave this location horizontally. In this instance, air tends to leave the upper atmosphere more quickly than it is replaced by air from lower down in the atmosphere. It is this net loss of air in a particular column that causes a reduction in pressure at the surface. As a result, air will ascend from the surface to the upper level, around area C. The second main process occurs nearer the surface and needs to work in conjunction with the upper air process that we have just described. Within the temperate latitudes, we have warm tropical air, meeting much cooler polar air. The boundary between these two different air masses is called the polar front. As with any boundary between two liquids, this will not be a continuous straight line. At some points along the front, we will find kinks, which are small irregularities along the front. What is happening in these kinks is that the warm tropical air is intruding into the cooler polar air. As the image sequence shows, this causes the warm air to replace cold air. This is an important point. If much lighter, warmer air replaces the colder, heavier air, then the surface pressure will drop, because we have reduced the total weight of the column. This particular process occurs quite regularly along the polar front. However, if this occurs underneath one of the upper air C zones, then the kink will develop further as warm air continues to replace cold air. This will eventually lead into the formation of a large-scale polar front depression. If we now look at the fully developed depression from above, we identify two unique surface features. The line with blue triangles on it identifies the first feature. This is called a cold front. This is where we have cooler, heavier air advancing and undercutting the warmer, lighter air. The advancing cold front will cause some of the warm air to rise up and over the cold air, but also force it to move, much like a bulldozer. The movement of this warmer air creates the second important surface feature. The line with the red semicircles on it identifies this second feature. We call this a warm front. This is where we have lighter, warmer air overriding heavier, cooler air. The warm air between these two fronts is called the warm sector. Its characteristics control the weather within the depression. If you remember from earlier, the low pressure was created from the intrusion of this warm air into the cold air, thereby reducing the surface pressure. Because this is essentially one of the main driving forces of the depression, some analysts have called these lows warm sector depressions, not polar front depressions. The movement of air, and therefore the wind within these depressions, is very different to the small-scale depressions. By knowing what the wind conditions are, we can better prepare for our flying. If the surface pressure is falling in the centre of a depression, then it goes to follow that air must move in horizontally. This is similar to the small-scale depression. However, what is different is that the surface flow doesn't quite get to the centre of the low directly. It appears to have a rotational flow around the centre as well, exactly like that of the tropical revolving storm. The reason that there is rotational flow around the low pressure is due to the Earth's spinning. The spinning or rotation of the Earth will cause air moving into the low to be either deflected to the right in the northern hemisphere or to the left in the southern hemisphere. This apparent force creating this deflection is known as the Coriolis force. It is sometimes referred to as the geostrophic force. In summary, we can say that air moves around these large-scale low pressures anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. Now we have seen how the air flows around such large-scale systems, let's now see what we might expect the weather to be like. The depression weather can be subdivided into the warm front and the cold front. Looking at the cross-section of a polar front depression, let's now take a look at the warm front, since it will be this part of the depression that will arrive first. We stated earlier that at the warm front we have warm, moist air being forced to rise over and above cooler, denser air. As this air rises up and along the front, the temperature will drop because of adiabatic cooling. This may cool the air to the dew point and condensation will occur. As a result, clouds will form along the front. Because the slope of the warm front is so shallow, roughly 1 in 150, the clouds that are developed have a broad horizontal appearance and are therefore more commonly stratiform cloud. This means layered type. These clouds can extend up to 600 nautical miles away from the surface position of the front. Looking along the front, note that at lower levels the cloud is much thicker and denser than those at higher levels. Therefore, if a warm front were to approach an area, we would see the cloud lowering and thickening. Firstly, we would notice the thin cirrus cloud at very high altitude, then the thicker cirrostratus, followed by the lower altostratus, and finally, right before the front approaches, the larger, thicker nimbostratus. This is one of the most obvious ways of recognizing an approaching warm front. As a result of the slope of the front and the horizontal spread of the cloud, the precipitation would cover a very wide area in front of the front, maybe a few hundred miles. As the front got closer, we would encounter increasing amounts of precipitation. This may be light and intermittent at first, but just in front of the warm front, where the cloud is lowest and thickest, we may encounter much heavier, continuous precipitation. The type of precipitation is another important point. Because the air along the front is rising relatively gently, there is only moderate vertical uplift. It is therefore common to find a mixture of fine rain and drizzle, or perhaps snow if the temperature is low enough, falling ahead of the warm front. In special cases, freezing rain or rain ice may fall, but we shall look at this later. Other important issues for aviation are the icing and turbulence that may be encountered along the warm front. The icing will generally be light along the warm front because of the lack of vertical support. However, with orographic intensification, the vertical support is increased and the freezing level can drop. Under these circumstances, the icing can be very dangerous. It is essential then to analyse your location to point out potential intensification. Under special circumstances, the most severe form of icing can be found underneath the warm front. This is known as freezing rain or rain ice, but as we mentioned earlier, this will be discussed in detail within the icing lesson. Turbulence along the warm front can be explained in a similar manner to icing. Because of the lack of vertical motion, the horizontal passage of an aircraft through the warm front would not abruptly change. We would most probably expect moderate turbulence within the lower clouds and light turbulence within the higher clouds. Finally, we will look at the surface horizontal visibility. Precipitation intensity increases as the front approaches, from light drizzle underneath the altostratus clouds to eventually moderate or even heavy rain beneath the nimbostratus at the front itself. Because of this, the visibility will decrease significantly as the front approaches. Fog can also be found before the front approaches, sometimes 200 nautical miles ahead of the front. This is known as frontal fog, and will be discussed in detail in the visibility lesson later on. The next section to look at will be the warm sector. Within this area of the polar front, we can generally find low cloud, such as stratus and stratocumulus, and occasionally advection-type fog. The reason for the cloud is because the warm air has come from the tropics. Therefore, it has had to pass over cooler land and waters. As a result of this, the bottom part of the air mass, which is in contact with the surface, will be cooling, and the air will be condensing, creating the cloud and fog. However, this is only happening at the surface. The rest of the warm sector above hasn't been cooling, and would therefore be mostly clear of cloud and weather. The next main weather of the polar front depression is the cold front. We stated earlier that at the cold front we have cold air undercutting warm air. The warm air is being forced to rise over and above cooler, denser air. As this warm air rises along the front, the temperature will drop because of adiabatic cooling. This may cool the air to the dew point and condensation will occur. As a result, clouds will form along the front. The slope of the cold front is a little steeper than the warm front. This slope is still quite shallow, and the clouds created by the rising air would still be layer type. But there is an important difference. When looking at the cold front at the surface, we see the front comes forward first, then starts to slope backwards. This nose of cold air is up to about 9,000 feet. This creates a unique effect. When cold air is found above warm air, that area can become very unstable. This means that the air has a potential for strong vertical movement. Convection will take place if the warm air rises into the cold air. This warmer air will now be much lighter than the air surrounding it and will rise just like a balloon. Therefore, we could find vertical or convective cloud concealed within the layered cloud. It is quite common to find large cumulus, cumulonimbus, or even thunderstorms embedded within the cold front. These are potentially dangerous clouds to aircraft operations, and the weather on the cold front will now be discussed. The precipitation on the cold front will be varied because of the mixture of cumulus and stratiform cloud. So not only could we get intermittent and continuous precipitation, but most probably some heavy showers, and even hail from the convective cells. Associated with these heavy showers, we might get some strong gusty winds as the air is dragged down towards the ground by the precipitation. Even at altitude, we would have to be very careful indeed. The turbulence could be quite severe, especially within the convective cells along the front. It is much the same with icing. Generally, light to moderate icing would be experienced, but within the convective cells there might be increased vertical support. This would enable greater quantities of large supercooled water droplets to be suspended. This could lead to severe icing within the convective cloud. Let's now look at what visibility we might expect. At the cold front, within areas of the precipitation, the visibility would be poor, especially within heavy rain. But outside the precipitation, lastly, we look at the weather behind the cold front. Air here has come from higher oceanic latitudes and will generally be cool and relatively drier than the warm sector. However, the air here is moving towards the equator and therefore travelling towards lower, much warmer latitudes. This will warm the lower layers of the air and cause it to become less dense and rise, or, as we can say, become unstable. This instability leads to, as we have seen, this convection leads to showery precipitation, with possibly hail as well. Again, turbulence and icing could be a problem within these areas. This now concludes the breakdown of the polar front depression. We can see that looking at the main weather within polar front depressions, there is a lot of information to absorb and understand. The weather is complex and variable, But by breaking down the weather and the aviation hazards into the warm and cold fronts, hopefully you will have a better understanding as to what is going on. We will cover these depressions again in a separate lesson, and all these points will be recapped later.